Welcome back to Honors Calculus. In this video, we're going to be talking about surface area, and we'll be specifically looking at surface area for a parametric surface. As we've done in our previous discussion of parametric surfaces, I want to use analogies to parametric curves that we've studied in depth in the past. Let me get my head out of the way and I'll show you exactly what I mean. When we studied the arc length of a parametric curve, r of t, we broke the curve down into tiny pieces, which I'm going to exaggerate as relatively large pieces. But we found out that each of those pieces was a vector r prime of t dt. And so when we're thinking about, sorry, getting ahead of myself, we found that we set ds as the magnitude of r prime of t dt, and then we could calculate the arc length by integrating all of those infinitesimally small pieces of the arc, right? So find the vector, find its magnitude, integrate those. When it comes to surface area, our tactic is going to be very similar. Except that our surface has two directions to it. But if we're looking at one piece, and I'm going to pretend that this is an infinitesimally small piece, although I'm drawing it quite a bit bigger, I can figure out that the length on one side of this thing is going to be partial r partial u du. And the length on the other side is going to be partial r partial v dv. And so I have tools for the two sides of this figure. If the figure is a rectangle, then I just want to multiply those two sides together. Although the challenge with that is that these two sides are both vectors, not scalars. And so when you multiply two vectors together, you have to make a choice. Do you want to use the dot product? Do you want to use the cross product? Or do you want to do something else? We haven't gotten into it in depth in this course, but when it comes to thinking about area enclosed by vectors, the cross product is the tool that we want to use. You can convince yourself of that by thinking about the fact that the cross product of these vectors is the thing that allowed us to find, find the equation of the plane. And when we're thinking about area, we're thinking about this tiny piece as being a plane. So I want to take partial r partial u du, and I want to cross it with partial r partial v dv. And that will give me a vector that describes the area. The direction of the vector is going to be sticking out of the surface. But the thing that I care about, if what I care about is surface area itself, is going to be the magnitude. All right, so I can define a vector surface, d vector s, and just rearranging this a little bit. Partial r, partial u cross partial r, partial v du dv. And if I want a scalar surface, ds is just going to be the magnitude of partial r, partial u cross partial r, partial v, du dv. And so with that, I have a tool for finding the area of a surface defined parametrically. And since I can take surfaces defined by other means and rewrite them as parametric surfaces, I have a tool for finding the surface area in general. So as an example, let's look at a surface similar to one that we've looked at before. Here I'm going to have r of u and v equal to 3u cosine v, 3u sine v, u squared. This is going to be similar to the elliptic paraboloid we've looked at before, but because now my coefficients here match and are both 3, instead of being an ellipse in its cross section, it's actually going to be a circle. And that difference is going to take this from a nightmare of integration to something not too bad. But to find the area of this, I guess we still need the constraints. So we have 0 less than or equal to u less than or equal to 2. And we have 0 less than or equal to v less than or equal to 2 pi. But we'll need the partial derivatives. Partial of u, or partial of r with respect to u has components 3 cosine v, 3 sine v, 2u. And partial of r with respect to v is going to have components negative 3u sine v, 3u cosine v, and 0. When we were finding the equation of a tangent plane, we were able to evaluate these partial derivatives at a point and then take a cross product. Unfortunately, with surface area, that doesn't quite work. So we have to take the cross products of these as functions. Computationally, it is messier, but it is the exact same process. We have I, j, k across the top row, the components of partial with respect to u, 3 cosine v, 3 sine v, 2u, and the components of the partial with respect to v, negative 3u sine v, 3u cosine v, and 0. And then we use cofactor expansion. In the I direction, we'll have 3 sine v times 0, which is 0, minus 3u cosine v times 2u, which is 6u squared cosine v. In the j direction, we'll have 3 cosine v times 0, which is 0, minus negative 3u sine v times 2u, which is going to be plus 6u squared sine v. And then in the k direction, I don't quite have enough space here, so let's go to a new line. I'll have 3 cosine v times 3u cosine v, which is 9u cosine squared v. Then minus, we have a negative 3u cosine v times 3u sine v. Negative, subtracting a negative is adding 9u sine squared v. And so that's negative 6u squared cosine v in the I direction. That's negative 6u squared sine v in the j direction. And hey, look at that. We have a cosine squared and a sine squared. Sine squared plus cosine squared is 1. So 9u cosine squared plus 9u sine squared is just 9u in the k direction. Continuing onward, we're not interested in just this cross product. We actually want the magnitude. So we want to take the square root of the sums of squares of components here. So we're going to take 6u squared cosine v. So it's going to give me 36u to the fourth cosine squared v. Then we'll have negative 6u squared sine v squared is 36u to the fourth sine squared v. And then we'll have that 9u, which is going to give me 81u squared. And what do you know? Once again, we've got a sine squared, we've got a cosine squared. Adding those things together gives me 1. So I've got here the square root of 36u to the fourth plus 81u squared. And I could leave it at that, but I'm going to notice that there's a common factor of 9u squared in both of these terms that I can factor out. And doing that now is going to make my life a little bit easier later. So I've got a common factor of 9u squared, and when I factor that out, it leaves behind 4u squared plus 9. And having that is going to make my life an awful lot easier when it comes to the next step. Because the next step is to say that the total surface area is the integral on the entire domain of the surface of ds. So it's going to be the integral. U goes from 0 to 2, integral. V goes from 0 to 2 pi of this magnitude, 3u square root of 4u squared plus 9. And I wrote it in the order dv du. I could have written it as du dv. It doesn't really matter, because notice that there's nothing with either u or v in the limits of integration, so I can actually split this up into two completely separate integrals. The integral from 0 to 2 pi of dv, and the integral from 0 to 2 of 3u square root of 4u squared plus 9 du. The most confusing thing about doing this integral is that I want to do a u substitution, but I've already got u going on. I've already got v going on, so I need some other dummy variable. How about t? T equals 4u squared plus 9, so dt is going to be 8u du. We've got 3u, we need 8u. That's just a factor of 3/8 extra. All right, so we can separately look at the integral from 0 to 2 pi of dv, and the integral, well, if I plug in u equals 0, I get t equals 9, and if I plug in u equals 2, I get that t equals 25. And we've got that 3/8 that I said was going to show up so that we can get the 8 inside. And then we've got the square root of t dt. Right. Integral on dv is just v. Integral on the square root of t is 2/3 t to the 3/2 power. What am I doing? getting ahead of myself. All right, v evaluated at 2 pi and at 0 gives me 2 pi. Then we've got 3/8. Then we've got 2/3. Then we've got, well, 25 to the 3/2 power. Square root of 25 is 5. 5 cubed is 125. 9 to the 3/2 power. Square root of 9 is 3. 3 cubed is 27. All right, so let's see. The 3's cancel out. Those two 2's cancel out with some of that in the 8. 2 pi times 3/8 times 2/3, all told, is pi over 2. And 125 minus 27 is 98. Half of 98 is 49. So the surface area of this shape is 49 pi. I want to point out quickly that we can turn this calculation of surface area very quickly into any of the applications of area integrals we've talked about previously. If we want to find the density, if we want to find the mass given the density, we just put a density function inside the integration and we continue on as we have been. Or anything else where we can determine what's happening in terms of the parameterization. For the sake of time, I'm not going to do that. Instead, I'm going to give you one more to try on your own. I apologize, the setup here is a little bit messy. Such is the nature of these surface integrals. Calculations get a little bit dense as you go through, but see what you can do with it. Get my head back out of the way and write out. So I would like you to calculate the surface area of a torus. This particular torus is going to be defined as having components 2 plus the cosine of u times the cosine of v, 2 plus the cosine of u times the sine of v, and sine of u for the z component. If you aren't familiar with the shape of a torus, I encourage you to use GeoGebra or something like that to graph this shape, see what I'm talking about. But the torus is essentially the donut shape, which is one of mathematicians' favorite shapes, it seems. And we're going to be looking here for 0 less than or equal to u less than or equal to 2 pi. And we also are going to have 0 less than or equal to v less than or equal to 2 pi. All right, so take a couple of minutes, see what you can come up with on that one, and I'll see you in the next video.